Hey everyone, so this is your week 7 lab 1 primer, and we're going to talk about the no operation or NOP sled. And it's referred to, of course, if we look at it in terms of assembly and in terms of, the actual code that it produces, we can detect the NOP sled by observing and looking for byte 90. All right. So that, just to put this into context, you recall that a program, and let's say it was written in .c. Okay, so it gets compiled into those machine, we'll call it MC or machine code, those ones and zeros. Now we can take a disassembler, and the disassembler will actually show the assembly instructions, or those little mnemonic keywords that disassemblers can produce. And what they're showing is snippets and clues of the assembly code that represents the specific instructions that the C code tells the machine to do when it gets compiled. Okay, so I'll just put D for disassembled code right here. And what we've been able to glean and understand about that is that one way that malicious code is written is that it can refer to an actual place in memory to do something, say, nefarious. Now, the machine or the CPU, since malicious code frequently can talk to directly to the CPU, it can give the CPU seemingly, you know, um, everyday instructions that it's not that big of a deal. For example, telling the CPU to add another character to the value, but the character that we're adding to the value might be something significant. So if we're trying to create a malicious invoice to a company, maybe a fake invoice, we can fool the bits that are created to create the original invoice, and we can fool it, for example, into making that the location of the in memory that held the balance. We can adjust the amount, but with a couple extra ones and zeros, and we can say that instead of you owing us $500, for example, you owe us $5,000 or something like that. So imagine you yourself giving the ability to artificially augment your bank account balance. Okay, of course we would never do that, because the very fact that we can possibly get in might leave a trace, and as they say, a artifact, and we might be caught. So anyway, so what is this, what I just had to say, have anything to do with the NOP sled? So if we presume that, the malicious code is going to reference a point in memory, here is the issue. The issue is that they have to be very precise about referencing that particular place in the victim's computer bank of memory addresses. Okay, so the no op instruction is an instruction that says basically you do nothing except occupy memory during runtime. Okay, and the thing is, think of it. Well, what does the fact that you're telling it to do nothing mean in the great world of possibilities? I mean, you're literally telling the computer, the processor, to do nothing. But instead, the idea is that if you look at malware as forcing a program to make a calculation or to add something at a particular address and then continue to run from there, okay, then the no op slide, or like for example, I show an example of a 128 byte NOP sled, instead of that victim or the nefarious code referencing one particular point in memory, you now have widened the target, if you will, such that if you reference any group of code, the NOP instruction will just formulate a slide, and then the slide will eventually be directed toward the malicious code. Now, one of the issues, even with the fact that the NOP sled allows you to widen the target in a big bank of memory slots, you still have the uh, the necessity of predicting about where the memory would be based on past implementations of the same program. And one of the issues is that we talked about last week the differences between stack and heap memory. So a lot of those variables, and keep in mind, a lot of enterprise level applications are written in for something called encapsulation, so that the instance variables or the stack variables are encapsulated within the methods themselves through the private access as opposed to public. So it's hard. It's nearly impossible to get in without actually referencing the actual physical place in memory. Okay, and the problem with that is even with the NOP slide possibilities enlarging that target, you have things like stack randomization that kind of put up a roadblock to say, hey, you presume it's going to be in this stack, but what if we randomized it, and instead of this stack, it's going to be one of a million uh, places in memory that it could be. The range could be in a number of different places. You're talking, if you've ever played the board game Battleship, okay, you know how difficult it is to predict where where your opponent's ship is. Now, if you do get a hit, it's obvious that you can possibly go one left. Hold on, sorry about this. Stay on call. I'm leveraging the Google Meet camera so you can still look at my ugly mug as a lecture. So, anyways, so it's like playing Battleship, in which if you say B12 and then he says you sunk my battleship, then if his ship is at B12, if one of the hits is B12. If you go to B11, his ship might also be there. So if you say B11, you might also get a hit. So that's the idea. But the problem is you predict based on past behavior of how the application actually runs, what slots in the actual memory that it will use. Of course, and we all know stack memory is temporary, so once the app is executed and done, then that's it. It won't go anywhere. However, those values will be deleted there, so that means that they're open to be used again, those slots. But the problem is with stack randomization, when the app is run again, the memory range might be something completely different. Okay, and so as I'm saying, the reason why, so what this does is it makes the NOP sled, you want it to be even bigger, encompassing more memory slots, so that if by chance when the app is run it hits anywhere in there, it can get slid into that malicious code. Now I do have a visualization slide coming up real soon. Now when it comes to location issues, as I said, the approximate location of the of the potential memory slot used for the malicious code has to be predicted in advance. And one method you could do that, and I kind of touched on this when I was in the other slide, is to see where the memory locations that were used were in the last instance, and then that gives you an idea of how wide you need to go in order to reasonably presume that you're going to hit it again within the first few tries. Now, if it's an app that's used a lot, then there's no reason why to think that you can possibly get another victim within the next few weeks or so if it's a high visibility application. Okay, and just so you know, on the x86 architecture, the NOP instruction is equivalent to hex byte OX90. Now the NOP slide inside malicious code, attackers. So what the strategy is that the attackers place long NOP chains, as they call them. They call them chaining prior to malicious payloads, so that if the app lands on those NOP memory locations, and a memory location that is inside the NOP code, it'll slide down and hit the malicious code. And NOP exploits are especially common and buffer overflow exploits. No, now we have such a thing as forensic evidence challenges. Okay, now one of the challenges of NOP slide is that there the raw or the specific NOP slide hack or malicious code does not in of itself generate network activity. Okay, now as I've kind of been teaching you, the defining aspect of things like persistence, like advanced persistence threat, that like the APT hammer toss. The one thing I have taught you is that malicious code and overall I'm going to say persistent threats do not act in isolation, right? We know that they don't. It's a layered attack. So chances are, if there is a malicious code built off of the NOP slide, it's going to then be a part of something more malicious. So you're talking like, for example, I just mentioned it before, buffer overflow exploits. So it's frequently going to break down the existing server, as an example. There's like memory artifacts, repeating OX90 bytes in memory dumps. Process artifacts such as crashes, like I just mentioned. File system evidence, dropped payload binaries, modified temporary files and execution logs. System logs, such as kernel logs showing illegal execution attempts. So the NOP slide does not leave network forensic footprints, but it does leave behavioral and structural footprints. So why might malware include NOP padding? It increases the reliability of the exploit. So you can pay millions of dollars, for example, for a DDoS attack, but if it doesn't hit, if the user never hits that place in memory, then the DDoS attack nothing more than almost like a zero day exploit, meaning that it may not even be detected by your semantic antivirus program or Kaspersky, if the definition that the malware has isn't in anyone's dictionary, right? So it's just sitting there. But what good is it if that part in memory is never hit by the application you want it to be hit by? So the NOP slide gives it a larger target. Stability. Okay, so it gives you more of a stable attack surface. Okay, and it allows you to be obfuscated because you can, for example, hide a malicious code in NOP operations because, quite frankly, legitimate applications also use the NOP sled for their own purposes. Okay. All right, so which layers of OSI would be observed? We have layer 7 if HTTP traffic was observed. So it is possible that a NOP slide can occur in conjunction with command and control. Okay, there's nothing wrong with that. Now, when I say there's nothing wrong, there's something ethically wrong, but I'm talking from a malicious standpoint. A what it would look like if it did have network traffic is, imagine if it was a command and control. Somebody downloads malware with a NOP sled. Finally, when the NOP sled is able to facilitate the malicious code is then receiving instructions. It probably sends out some sort of an acknowledgement beacon from the victim computer, and then it would then receive orders from some remote server. So when you think about that, the evidence reserve would be layer 7, the app. That would be, you would see HTTP type request headers and payload data. Transport, there would be evidence of the three-way handshake, right? Or as this slide calls it, the TCP handshake. The network would supply us with IP addresses. Data link would, of course, supply us with MAC addresses, and the physical would give us electrical signaling that may not be visible in Wireshark. Okay, so that is the type of information that it gives us. Of course, which MITRE attack technique aligns with, in this particular case, if there was a CNC, if there was a command and control activated by this piece of malware, what technique aligns with the packet capture validation, and that would be T1040 network sniffing. So a little bit about the MITRE attack. If you go to Google and Google MITRE attack, it'll lead you to the MITRE attack, website, and that gives you a column type reporting system, and I urge everyone to do that. You can see all the categories of vulnerability amongst all the different stages of exploitation, whether it's reconnaissance, whether it is capturing, and everything like that. So T1040 for network sniffing is a technique that involves monitoring or sniffing, quote unquote, traffic for the purpose of finding out what the heck is going on, looking for keywords, looking for hidden files, if you will. We're going to go through the certain aspects of Wireshark that you can modify the way your Wireshark looks to further detect little, I'm going to say, Easter eggs like that. So we can detect like things like the command and control with network sniffing, and the technique is T1040. Now there is, if the malware uses HTTP, we can also refer to T1071, the application layer protocol. Now, what are these T numbers? These are codes that MITRE attack uses to specifically describe a condition of either defending yourself or if it's an offensive attempt at exploitation. MITRE attack uses these codes because if we say it's a T1040, everyone knows what the notion of network sniffing is, as opposed to having to delineate what they mean by network sniffing. The reason why analysts must correlate host and network evidence is the fact that no one source of data is ever good enough. So let me just clue you in on something. I mean, as if you didn't already know, I'm sure you do. So I would never insult anyone's intelligence. But we ought to know by now that, even when you do things either statically or dynamically, even when you analyze malware statically or dynamically, we are limited by our tooling because a lot of times we don't see the original source code. If we saw the original source code, we can easily see what is going on because source code is written in, even C is written in somewhat abstract language, although Python is the most abstract language. It goes Python, Java, maybe C, and then the least abstract language that we can get our hands on is, of course, is assembly. And C is the only language that we can disassemble into something of that resembling the original assembly code, but even then, not sure. It's not exact. It's not a one-for-one science, I guess you could say. But because of that, because of limitations of both static and dynamic analysis, We can't rely on everything because even legit software has malicious code aspects. For example, Wireshark, okay, that is reliant on some of the communication protocols that are under it, and those communication protocols that have to analyze your packets as they are transmitting act like malicious code. So packet sniffers on one hand are malicious. On the other hand, Wireshark is one of the best packet sniffers out there, and it's free, and everyone uses it. So hopefully everyone understands that there is a little bit of a gray area here. So not one. There's no one source that tells us the complete story. Now, network evidence also shows us who communicated, when it occurred, and it gives us command signals. For example, if we're trying to detect a command and control exploit, if we can we can isolate the network voices by running it in a sandbox. So what I'm saying is that the reason why we do that, because if we run it live, then we can't nab, quote unquote, we can't blame and we can't analyze every single packet that's going out, because if you're working for a company with thousands of employees, it would there would be no possible way you can monitor everything. So that's why you take the suspected malware, you run it in a sandbox that's isolated, and making sure that there's no way the malware can get out, and then you observe it in isolation. So what I'm saying is that you're using multiple techniques, not just one, to try to determine what is going on. And if you only look at network data, like look at this lab coming up, where all we're doing is we're running the NOP sled. We are not teaming it up. We're not teaming up with any type of command and control type um, malware. So there is no network forensic activities to look at. Now, in the lab today, yes, we are going to bring up Wireshark momentarily as we run the exploit, but you're going to see there is no network activity. So if we only looked at network data, we would miss the local exploitation. Okay, and we would miss the lateral movement, I guess, or lateral opportunities that a malicious attacker would have. For example, the CrowdStrike attack that hit Steam, in which it may have robbed people of their armor that they paid for, but the real exploitation was that they were able to take their passwords and use social engineering to look at all their other accounts like Insta, Google, Gmail, YouTube, and all that, and Netflix, and they found out that a lot of people were using the same passwords. So there you have the lateral movements. So that if you didn't detect any network issues or network presence, network forensics presence, in that Steam attack, then you would have missed the fact that, hey, it's also grabbing passwords, and they're using the notion of the fact that it's the lateral vulnerability that we all have, because we kind of use the same password for all of our services. Now, the NOP slide, let me go ahead and correct that. What does it look like? It's a sequence of instructions that do nothing. So on an x86 system, it's going to be OX90. So instead of jumping to an exact address, attackers create a long chain of NOPs. So we have the memory looking at this NOP, 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 and then here's the payload. And if the execution lands anywhere here, it will naturally gravitate to the payload. Now let's take a look at today's lab. Okay. Well, actually, here's yet another example. We have this is like where it would be closely resemble a stack, NOP, 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 jump, payload, and then we have within the payload the malicious code. So the NOPs don't really do anything. They form the slide, which will eventually direct it to the malicious code. So what do host forensic people look for? They look for long instructions like this as a potential red flag. But as the 2 slides ago would say, there is no one piece of evidence that we can rely upon So because it could be that that this 90 might be utilized legitimately. So there are a lot of legitimate programs that also use the NOP slide for their legitimate purposes. So um, this might be a red flag, but just because it's a red flag doesn't necessarily mean it's malicious. Now let's take a look at this week's lab right here. The required tools is your existing Debian virtual machine. Now it could be Debian, it could be Ubuntu, you could be using another version of Debian. I don't care. Kali, I don't care. Just any Linux virtual machine. Obviously, it's going to come with a GCC compiler. My bad. Object dump, which is a program, and if you try to run it and it says you need to install it, then you'll have to install it. Of course, Wireshark and things like that. Step one is it directs you to create a binary right here. Now you're going to create a program called we'll use Vim. You're going to create a program called nop_demo.c. Okay, and this is the code right here, pound include standard in out dot head, and then it's going to continue. You're going to say int main, which is your main method right here, and then you're going to say print, and then that's F is for formatting, so it can include non-escapable characters or formatting characters like this backwards N. That gives that's for new line, NOP demonstration program, new line. Now ASM is a compiler-specific extension used to embed actual assembly language instructions directly within this C code. So ASM, and then you're going to add the NOP. This is like the NOP slide right here, and then it says program created successfully. The next step is you're going to compile and execute it. So that's gcc nop_demo.c, and then -o is what is the name of the program that is you could say that is the result of the GCC algorithm, and we'll just direct the compiler to call it nop_demo. Okay, now if you don't utilize the -o choice, it automatically just says a.out. So if you did an ls, you would just do a.out. Next, you're gonna run the NOP demo program, and then you are going to dump the program. This actually disassembles it, and then you're going to locate the repeated NOP instructions. You're going to record the addresses and surrounding instructions. You are then going to look at the host for Hensix window after you ran it, and you're going to do a PS, which prints out all the processes that would have NOP demo in it. Now the last slide is going to be the output. What does like that's right there? What does the PS aux do? It lists the processes per user and process ID number. So it lists out the processes. So the first one is the user owning the process. The process ID of the process and how much CPU and memory that it is using, okay, and what time it started and the time that it proceeded. So the cumulative CPU time. So you should pretty much be seeing all zeros when you run it on your end. Okay? All right, that's it. Thank you very much. And good luck with this week's lab.